In episode 1, we dropped a battery into lava and it exploded instantly. Heat is the obvious enemy, but what about the silent killer? This is liquid nitrogen. It boils at minus 196 degrees Celsius. It is colder than the surface of Mars, and this is a standard lithium-ion battery. The same kind found in every Tesla and iPhone on the planet. If heat makes a battery explode, will cold make it invincible? Or will we accidentally create a bomb? Let's start the simulation. Before we drop it, we need to understand the physics. Batteries work by moving ions through a liquid electrolyte. It's like a chemical river, but at this temperature, rivers don't flow. They freeze. Theoretically, if we drop this in, the battery should enter cryogenic sleep. The energy is still trapped inside, frozen in time, waiting to be woken up. This is why scientists want to use this tech for space travel. But theory is not reality. Simulation, ready. Dropping the power cell in 3, 2, 1. Contact. Look at the boil. The nitrogen is reacting violently. This is the Leidenfrost effect. The battery is so hot compared to the cold liquid that it creates a vapor shield, but watch the voltage meter. It drops to 0 instantly. The battery is dead. Now, listen to the sound. Crack. Snap. That isn't the chemistry. That is thermal contraction. The metal casing is shrinking. The plastic seals are shrinking. But they are shrinking at different rates. The battery is literally crushing itself from the outside in. Let's pull it out. It looks safe. It is covered in white frost. It feels like a solid brick of ice. If I hit it with a hammer, it shatters like glass. The liquid inside is frozen solid, but here's the twist. This is a zombie. As it sits on the table and warms up, the ice turns back into liquid electrolyte. But the separator, the microscopic wall that prevents short circuits, was shattered by the cold. It is gone. So, the moment it thaws, spark. Boom! The battery spontaneously combusts. We learned a terrifying lesson. You can't freeze the danger away, you just delay the explosion. This is why electric cars lose range in the winter, and why a battery damaged by cold is a ticking time bomb. We have frozen time. Now, we need to speed it up. We are going to simulate the ultimate battle, man-made trash versus Mother Nature. In the comments, vote for the next simulation. Option A, 100 years of trash versus nature, a time-lapse of decay. Option B, solar panel versus wind turbine. Which creates more power? The top comment decides the timeline. Subscribe for science. Class dismissed. Let's delve deeper into why extreme cold has such a catastrophic effect on batteries. Imagine the battery's internal components as a delicate network of pathways. These pathways facilitate the flow of ions, the lifeblood of a battery's energy. When exposed to liquid nitrogen's frigid embrace, these pathways undergo a dramatic transformation. The electrolyte, normally a fluid medium, solidifies into a frozen state. This impedes the movement of ions, effectively halting the battery's ability to discharge energy. Furthermore, the extreme temperature differential induces stress within the battery's structure. Different materials contract at varying rates, leading to internal fractures and structural compromise. The separator, a crucial component responsible for preventing short circuits, becomes brittle and prone to breakage. As the battery warms, the frozen electrolyte thaws, re-establishing the flow of ion. However, the compromised separator can no longer fulfill its protective function. This creates a pathway for uncontrolled electron flow, resulting in a sudden and violent release of energy. The battery essentially self-destructs in a fiery explosion. The lesson learned is that while extreme cold may temporarily halt a battery's function, it inflicts irreversible damage that ultimately leads to its demise. This phenomenon has significant implications for various applications, including electric vehicles. The reduced range experienced by electric cars in winter can be attributed to the electrolyte's increased viscosity. This hinders ion flow and diminishes the battery's overall performance. Moreover, repeated exposure to freezing temperatures can accelerate the degradation of battery components, leading to a shortened lifespan and increased risk of failure. Understanding the effects of extreme cold on batteries is crucial for developing strategies to mitigate these risks and ensure the safe and reliable operation of battery-powered devices. Further research and development efforts are needed to engineer batteries that can withstand extreme temperatures.